Hello everyone, once again welcome back to my YouTube channel. Now we are going to talk about the torque which is experienced by a dipole when it is placed in a uniform electric field. So we already know we have to focus on the diagram in order to complete the derivation. So first of all, which is the major requirement of us is a dipole and a uniform electric field. So let us take a dipole, that is a pair of equal and opposite charges separated by a very small distance. I will take this charge as plus q and this charge as minus q, and the separation between these two charges is very small, and that separation is taken to be 2a. So first of all, we will define our dipole like this. So 2a is representing a length of the dipole. Now the other thing which we need is a uniform electric field, and we know that uniform electric field is represented by the parallel lines separated by the same distance. So these lines are representing uniform electric field, and the dipole is making certain angle with this uniform electric field. Let me complete this diagram first of all. Right. So let us suppose that charge plus q is placed at point A and charge minus q is placed at point B. Now plus q charge will experience a force along the direction of the uniform electric field, that is F is equal to QE, and minus q charge will also experience a force, but this force will be along the direction opposite to the direction of the uniform electric field. So this will be in the direction this, that is F is equal to minus QE. Now these are the forces which are equal but are in opposite direction, and if we will extend the line of action for these forces, for plus q charge, line of action for F force is this particular direction which I have shown with the laser light, and for minus q each force, if we extend this particular line, the line will be in this particular direction. That means F is equal to plus QE and F is equal to minus QE are forming a couple because these two forces are equal and opposite, but their lines of action is also different. That is why the forces which are acting on plus q charge and minus q charge are equal and opposite and acting along the different line of action. Therefore, these forces constitute a couple. Now, we will write that magnitude of either force is equal to QE magnitude, or it is equal to minus QE taken in magnitude. That means F is equal to QE. So this is our first equation. Also, the area of interest is to calculate the value of the distance between these two forces which are equal and opposite and have a different line of action. And in order to do that, what we will do, we will just try to extend these two lines in our imagination, and we just need to drop a perpendicular over here, so we will be able to find the perpendicular distance between these two forces. So dropping a perpendicular from this particular point, we will be able to find this perpendicular distance between these two lines of action. So let us say this dipole is making an angle theta with the direction of uniform electric field. As the area of interest is to calculate AC, because we need to know what is the distance between the force which is acting on along the direction, this particular direction, and the distance for the force which is acting along this particular direction. So that means my area of interest is to find the distance AC, and in order to find the distance AC, which trigonometric function is going to help? Let us check it out. So AC is a perpendicular. How I have calculated it, how I have judged that AC is perpendicular? Because in order to locate a perpendicular, we have to find the angle Angle is over here, angle theta is with line AB, which is making with BC. So in front of angle we always have a perpendicular, so AC is a perpendicular, and we already know the value of hypotenuse, that is AC. Therefore the trigonometric function which is going to help us out is sine theta. So sine theta is equal to perpendicular upon hypotenuse, and from this diagram it is clear that perpendicular is equal to AC and hypotenuse is AB. Therefore AC we have to calculate it, we have to find out its value, and AB is already known to us, that is 2A. So this implies AC is equal to 2A sine theta. So this is the equation which we are going to need later on. But what our article says that we are having an area of interest over torque, that is we just need to calculate the amount of torque experienced by the pair of equal and opposite charges separated by a very small distance. So recalling the definition of torque, we know torque is defined as product of force, magnitude of force, and the perpendicular distance between the two forces. So we have tau is equal to r cross f, or in terms of magnitude only I could say tau is equals to rf, and for value of force we are having a magnitude of force as QE and the perpendicular distance is AC. So the perpendicular distance is always taken from the axis of the rotation. In this case we are having a perpendicular distance AC multiplied by F, and we can easily substitute the values of AC and F. AC is equal to 2A sine theta and F is equals to QE, that is Q into E. So we have tau is equal to, that is torque is equals to 2A Q E sine theta. Now once again recalling the value, the definition of dipole moment. The dipole moment is defined as length of the dipole multiplied by magnitude of either charge. So P is equals to 2AQ. That is why I can easily replace 2AQ with the P, that is dipole moment. So tau is equals to PE sine theta. And once again going back to the class 11th concept, whenever we have a component sine theta we always take a cross product. So in terms of vector product I could define it as tau vector is equals to P vector cross E vector. So this is the amount of torque which is experienced by the dipole when it is placed in a uniform electric field. But we need to discuss some of the special cases. So first special case is when theta is equals to 0 degree. So if theta is going to be 0 degree, then what will be the value of torque? Tau is equals to PE sine 0. So instead of writing theta I will put 0. So we know sine 0 is 0. Therefore whole term is 0, because sine 0 is 0, then whole term is going out to be 0. This implies torque experienced by dipole is 0. That is dipole is not experiencing any kind of torque, and we will call a dipole into a stable equilibrium. So this is a condition of stable equilibrium. Next condition is if theta is equals to 180 degree. If theta becomes 180 degree, tau is equals to PE sine 180. Again, we know sine 180 is 0. Therefore, 0 multiplied by P and E is going to be 0. So, tau is equal to 0. This implies again we have torque experienced by the dipole is equal to 0. But in this case, our dipole will be under unstable equilibrium. And the last thing we need to discuss, that if dipole makes an angle of 90 degree, if theta is equals to 90 degree, then torque is equals to Pe sine 90, and we already know sine 90 is 1. Therefore, we can write it as Pe multiplied by 1. Answer is Pe. This implies we can say torque is equals to Pe, which is the maximum value of torque acting on the dipole when it is perpendicular to the uniform electric field. So this is the article related to the torque experienced by a dipole when it is placed in a uniform electric field. I hope you have understood the concept, and if you like the video, please do not forget to press subscribe, like and share button, and do press the bell icon